Most of the information from this lecture has been adapted from Parallel Programming, Techniques and Applications Using Networked Workstations and Parallel Computers, 2nd edition, by Barry Wilkinson and Michael Allen. So in this lecture we'll be having these three topics: partitioning, divide and conquer, and then putting them together into an example. We'll go through each one of them one by one. Partitioning divides the problem into parts. It is the basis of all parallel programming in one form or another. The embarrassingly parallel problems that we've talked about earlier used partitioning without any interaction between the parts. Most partitioning formulations, however, require the results of the parts to be combined to obtain the desired result. Partitioning can be applied to the program data. That means to divide the data and operating upon the divided data concurrently. This is called data partitioning or domain decomposition. Partitioning can also be applied to the functions of a program, which means dividing it into independent functions and executing them concurrently. This is functional decomposition. The idea of performing a task by dividing it into a number of smaller tasks that, when completed, will complete the overall task is of course well known and can be applied in many situations, whether the smaller tasks operate upon parts of the data or are separate concurrent functions. It is much less common to find concurrent functions in a problem, but data partitioning is a main strategy for parallel programming. There are many different possibilities for the divide and conquer or partitioning technique. Here are some of the examples. You might have a large collection of numbers that you need to add together. Normally, in a sequential situation, you would have to go through the whole list on one processor and add them one by one. But in a divide and conquer or partitioning situation, you could have the list divided into several parts and a different process deal with each part. Another common problem is sorting. There are many different sorting algorithms out there, and some of them naturally can be done in a recursive fashion. This means that it might be possible to have the different recursion done by a different processor. Another common problem is numerical integration. Normal numerical integration on one processor would mean that the same processor would have to calculate each point for the integration and add them all together. In a multiprocessor environment, then, this means that parts of the integration can be done by different processors. Another problem is to calculate orbits based on gravitational forces for many bodies. This involves a lot of computation, and it would be helpful to be able to split up the problem into many processes to speed up the solution. Suppose a sequence of numbers x0 to xn minus 1 are to be added. We might consider dividing the sequence into t parts of n divided by t numbers each. x0 to xn divided by m minus 1, then xn divided by n to x2 2n divided by m minus 1, and so on, as you can see in the diagram. So then, if you have p processors, then each processor could add one of the sequences independently. to create partial sums. The p partial sums need to be added together to form the final sum. Note that each processor requires access to the numbers it has to accumulate. In a message passing system, the numbers would need to be passed to the processors individually. In a shared memory system, each processor could access the numbers it wanted from the shared memory. And in this respect, a shared memory system would clearly be more convenient for this and similar problems. The parallel code for this example is straightforward. For a simple master-slave approach, the numbers are sent from the master processor to the slave processors. They add their numbers, operating independently and concurrently, and send the partial sums to the master processor. The master processor adds the partial sums to form the result. Often, we talk of processes rather than processors for code sequences where one process is best mapped into one processor. It is a moot point whether broadcasting the whole list of numbers to every slave or only sending the specific numbers to each slave is best, since in both cases, all numbers must be sent from the master. The specifics of the broadcast mechanism would need to be known in order to decide on the relative merits of the mechanism. A broadcast will have a single startup time rather than separate startup times when using multiple send routines and may be preferable. First, we will send the specific numbers to each slave using individual sends. Given n numbers divided into p groups, where n divided by p is an integer and one group is assigned to one slave process, there would be p slaves. The code using separate sends and receives might look like what is shown on the screen here. If a broadcast or multicast routine is used to send the complete list to every slave, code is needed in each slave to select the part of the sequence to be used by the slave, adding additional computational steps within the slave. This code on the screen illustrates this. Slaves are identified by a process ID, which usually can be obtained by calling a library routine. Most often, a group of processes will be first formed, and the slave number is an instance or rank within the group. The instance or rank is an integer from 0 to m-1, where there are m processors in the group. MPI requires communicators to be established, and processors will have ranks within a communicator. Groups can be associated within communicators, and processors have a rank within the group. If scatter and reduce routines are available, as in MPI, the code might look something along these lines as shown on the screen. Please note that all the code shown in this particular set of slides are only pseudocode, because the actual MPI code will have a lot more parameters, including source and destination IDs and so on, which would clutter up the slide. That is why these slides use pseudocode to get the idea across without the additional details of the code. Normally, the operation of a reduce routine will be specified as a parameter and not as part of the routine name as shown here. Using a parameter does allow different operations to be selected easily. Code will also be needed to establish the group of processes participating in the broadcast, scatter, and reduce. Although we are adding numbers, many other operations could be performed instead. For example, the maximum number of the group could be found and passed back to the master in order for the master to find the maximum number of all those passed back to it. Similarly, the number of occurrences of a number or character or string of characters can be found in groups and passed back to the master. We make our analysis throughout the separate communication and computation. It is easier to visualize if we also separate the actions into distinct phases. As with many problems, there is a communication phase, followed by a computation phase, and these phases are repeated. First, we need to consider the communication aspects of the P slave processes reading their n divided by p numbers. Using the individual send and receive routines requires the computation time shown in the part of the slide that says Phase 1 Communication. In this part, T startup is the constant time portion of the transmission, and T data is the time to transmit one data word. Using scatter might reduce the number of startup times. However, in any event, the time complexity is still O of n. Next, we need to estimate the number of computational steps. The slave processes each add n divided by p numbers together, requiring n divided by p minus 1 additions. Since all p slave processes are operating at the same time, we can consider all the partial sums obtained in the n divided by p minus 1 steps. Hence, the parallel computation time of this phase is shown by the part of this slide labeled Phase 2, Computation. Returning partial results using individual send and receive routines has a communication time as shown in the part of this slide labeled Phase 3. For the final accumulation, the master has to add the p partial sums, which requires p minus 1 steps, as shown in the part of this slide labeled Phase 4. The overall execution time for the problem using send and receive is shown in the part of this slide labeled Overall. We see that the parallel time complexity is the same as the sequential time complexity of O of n. Of course, if we consider only the computational aspect, the parallel formulation is better than the sequential formulation. In case you're wondering why we bother to do parallel computation then, the problem with this example is that we are merely asking for additions. Additions do not take very much time, and the time it takes to send all the data to the other processes may overwhelm the amount of time taken for the additions. In a general situation, where the amount of computation done is much bigger, then it would often be worthwhile splitting up the problem into multiple processes. The divide and conquer approach is characterized by dividing a problem into sub-problems that are of the same form as the larger problem. Further divisions into still smaller sub-problems are usually done by recursion, a method well known to sequential programmers. The recursive method will continually divide a problem until the task cannot be broken down into smaller parts. Then, the very simple tasks are performed and results combined, with the combining continued with the larger and larger tasks. Here is a sequential recursive definition for adding a list of numbers. As in all recursive definitions, a method must be present to terminate the recursion when the division can go no further. In the code, the function number returns the number of numbers in the list pointed to by s. If there are two numbers in the list, they are called n1 and n2. If there is one number in the list, it is called n1 and n2 is 0. If there are no numbers, both n1 and n2 are 0. Separate if statements could be used for each of the cases 0, 1 or 2 numbers in the list. Each would cause termination of the recursive call. This method can be used for other global operations on a list, such as finding the maximum number. It can also be used for sorting a list by dividing it into smaller and smaller lists to sort. Merge sort and quick sort sorting algorithms are usually described by such recursive definitions. One would never actually use recursion to add a list of numbers when a simple iterative solution exists. But the following is applicable to any problem that is formulated by a recursive divide and conquer method. When each division creates two parts, a recursive divide and conquer formulation forms a binary tree. The tree is traversed downwards as calls are made and upward when calls return. A pre-ordered traversal given the recursive definition. The information on this slide has already been discussed and is provided here for you in written form. This diagram shows a binary tree construction showing the divide part of a divide and conquer, with the final tasks at the bottom and the root at the top. The root process divides the problem into two parts. These two parts are each divided into two parts, and so on until the leaves are reached. There, the basic operations of the problem are performed. This construction can be used in the preceding problem to divide the list of numbers first into two parts, then into four parts, and so on, until each process has one equal part of the whole. After adding pairs at the bottom of the tree, the accumulation occurs in a reverse tree construction. Here, we see a complete binary tree, that is, a perfectly balanced tree with all the bottom nodes at the same level. This occurs if the task can be divided into a number of parts that is a power of 2. If it cannot, then one or more bottom nodes will be at one higher level than the others. For simplicity, in this example, we will assume that everything can be divided by a power of 2. The information on this slide has already been discussed and is provided here for you in written form. The information on this slide has already been discussed and is provided here for you in written form. In a sequential implementation, only one node of the tree can be visited at a time. A parallel solution offers the prospect of traversing several parts of the tree simultaneously. Once a division is made into two parts, both parts can be processed simultaneously. Though a recursive parallel solution could be formulated, it is easier to visualize it without recursion. The key is realizing that the construction is a tree. One could simply assign one processor to each node of the tree. That would ultimately require 2 to the power of n plus 1 minus 1 processors to divide the task into 2 to the power of m parts. Each processor would only be active at one level in the tree, leading to a very inefficient solution. A more efficient solution is to reuse processors at each level of the tree, as illustrated in this picture, which uses 8 processors. The division stops when the total number of processors is committed. Until then, at each stage, each processor keeps half of the list and passes on the other half. First, P0 communicates with P4, passing half of the list to P4. Then, P0 and P4 pass half of the list they hold to P2 and P6, respectively. Finally, P0, P2, P4, and P6 pass half of the list they hold to P1, P3, P5, and P7, respectively. Each list at the final stage will have n divided by 8 numbers, or n divided by p in the general case of p processors. There are log p levels in the tree. The information on this slide has already been discussed and is provided here for you in written form. The information on this slide has already been discussed and is provided here for you in written form. The combining act of summation of the partial sums can be done as shown in this diagram. Once the partial sums have been formed, each odd-numbered processor passes its partial sum to the adjacent even-numbered processor. That is, P1 passes its sum to P0, P3 to P2, P5 to P4, and so on. The even-numbered processors then add the partial sum with its own partial sum and pass the result onward, as shown. This continues until P0 has the final result. Incidentally, these constructions are the same as a binary hypercube broadcast and gather algorithm. The constructions would map into a hypercube perfectly, but they are also applicable to other systems. As with the hypercube broadcast gather algorithms, processors that are to communicate with other processors can be found from their binary addresses. Processors communicate with processors whose addresses differ in 1 bit, starting with the most significant bit for the division phase and with the least significant bit for the combining phase. The information on this slide has already been discussed and is provided here for you in written form. The algorithm on this slide illustrates what we had earlier discussed. Suppose we statistically create 8 processors to add a list of numbers. The code on this slide illustrates what process P0 might do. Similar sequences are required for the other processes. Clearly, another associative operator, such as multiplication, logical OR, logical AND, minimum, maximum, or string concatenation can replace the addition operator in this example. The basic idea can also be applied to evaluating arithmetic expressions where operands are connected with an arithmetic operator. The tree construction can also be used for such operations as searching. In this case, the information passed upward is a Boolean flag, indicating whether or not the specific item or condition has been found. The operation performed at each node would be an OR operation in this case. This slide shows an example of what process P4 might do in the example that we have been discussing. So, how much time does this all take? We shall assume that n is a power of 2. The communication setup time, T startup, is not included in this slide for simplicity. The division phase essentially consists only of communication if we assume that dividing the list into two parts requires minimal computation. The combining phase requires both computation and communication to add the partial sums received and pass on the result. There is a logarithmic number of steps in the division phase, that is, log p steps with p processes. The communication time for this phase is given by the formula shown under the label division phase. In this formula, T data is the transmission time for one data word. The time T,1 is marginally better than a simple broadcast. The combining phase is similar, except that only one data item is sent in each message, the partial sum. So the formula for this is shown under the label combining phase. This makes the total communication time the formula shown under the label total communication time. This means that the time complexity is O of n for a fixed number of processors. At the end of the divide phase, the n over p numbers are added together. Then, one addition occurs at each stage during the combining phase, which gives us the formula shown under the label computation. The time complexity for this is again O of n for a fixed number of processors. If n is large and variable p, then we get O of n divided by p. This results in the overall execution time in the formula shown under the label total parallel execution time. The very best speedup we could expect with this method, of course, is p, where all p processes are computing their partial sums. The actual speedup will naturally be less than this due to the division and combining phases. This slide illustrates the example we mentioned earlier, where the tree construction can be used for such operations as searching, and so the information passed upward is a Boolean flag, indicating whether or not the specific item or condition has been found. Therefore, the operation performed at each node is an OR operation. Don't think that divide and conquer only applies when you split each part into two. For example, if you're trying to process a photo, you might need to split it up into 4 because a photo is two-dimensional, and so slicing a photo in two horizontally and vertically would give you 4. This results in a tree we call a quad tree, quad meaning 4. Here is a picture of a quad tree. Here is a picture of a recursively divided image, like the example I mentioned earlier. To place a number into a specific bucket, it is necessary to identify the region in which the number lies. One way to do this would be to compare the number with the start of region. That means a divided by m, 2a divided by m, 3a divided by m, and so on. This could require as many as m-1 steps for each number on a sequential computer. A more effective way is to divide the number by m divided by a, and use the result to identify the bucket from 0 to m-1, one computational step for each number. Although division can be rather expensive in time, if m divided by a is a power of 2, one can simply look at the upper bits of the binary number. For example, if m divided by a is 2 to the power of 3, that means 8, and the number is 11000101 in binary, it falls into the region 110, meaning 6, by considering the most significant 3 bits. In any event, let us assume that placing a number into a bucket requires one step, and that placing all the numbers requires n steps. If the numbers are uniformly distributed, there should be n divided by m numbers in each bucket. Next, each bucket must be sorted. Sequential sorting algorithms, such as quicksort or merge sort, have a time complexity of O of n log n to sort n numbers. For quicksort, this is the average time complexity and not the worst time complexity, because quicksort's worst time complexity is O of n squared. However, fortunately, quicksort seldom, if ever, hits that worst complexity because of the low probability of it happening. The lower bound on any compare and exchange sorting algorithm is about n log n comparisons. Let us assume that the sequential sorting algorithm actually requires n log n comparisons, one comparison being regarded as one computational step. Thus, it will take n divided by m log n divided by m steps to sort the n divided by m numbers in each bucket using these sequential sorting algorithms. The sorted numbers must be concatenated into the final sorted list. Let us assume that this concatenation requires no additional steps. This means that if we combine all the actions, the sequential time becomes O of n log n divided by m. If n equals km, where k is a constant, then we get a time complexity of O of n. Note that this is much better than the lower bound for sequential compare and exchange sorting algorithms. However, it only applies when the numbers are uniformly distributed. Clearly, bucket sort can be parallelized by assigning one processor for each bucket. This implementation is illustrated on this slide. In this version, each processor examines each of the numbers so that a great deal of wasted effort takes place. The implementation could be improved by having the processors actually remove numbers from the list into their buckets so that they are not reconsidered by other processors. The information on this slide has already been discussed and is provided here for you in written form. We can further parallelize the algorithm by partitioning the sequence into M regions, one region for each processor. Each processor maintains P small buckets and separates the numbers in its region into its own small buckets. These small buckets are then emptied into the P final buckets for sorting, which requires each processor to send one small bucket to each of the other processors, bucket I to processor I. The overall algorithm is shown in this picture. Note that this method is a simple partitioning method in which there is minimal work to create the partitions. These phrases are thus needed. First, partition numbers. Second, sort into small buckets. Third, send to large buckets. And fourth, sort the large bucket. The information on this slide has already been discussed and is provided here for you in written form. This picture illustrates the sending of the many small buckets from each processor to the buckets of each other processor. This picture shows what happens when you do an all-to-all transfer. Let us now look at how long it takes. The first step is to send groups of numbers to each processor. Marking a group of numbers into partitions can be done in constant time. Rather than make the partitions and then send a partition to each processor, a more efficient solution is to simply broadcast all the numbers to each processor and let each processor make its partition. One must ensure that each partition so created is disjoint, but the partitions together include all the numbers. Using a broadcast or scatter routine, the communication time is as shown in the formula labeled phase 1. To separate each partition of n divided by p numbers into p small buckets requires the amount of time shown by the formula under the label phase 2. Next, the small buckets are distributed. There is no computation in phase 3. Each small bucket will have about n divided by p squared numbers, assuming uniform distribution. Each process must send the contents of p-1 small buckets to the other processors, one bucket being held for its own large bucket. Since each process of the P processors must make this communication, if these communications cannot be overlapped in time and individual sends are used, the lower bound would occur if the communications could overlap, leading to the formula shown under the label phase 3. In essence, each processor must communicate with every other processor, and an all-to-all mechanism would be appropriate. An all-to-all routine sends data from each process to every other process, as illustrated earlier. This type of routine is available in MPI all-to-all, which we assume would be implemented more efficiently than using individual sends and receives. The all-to-all routine will actually transfer the rows of an array to columns, as illustrated in the earlier slide. So, in the final phase, the large buckets are sorted simultaneously. Each bucket contains about n divided by p numbers, hence the formula shown under the label phase 4. The overall execution time, including communication, is shown under the label overall. It is assumed that the numbers are uniformly distributed to obtain this result. If the numbers are not uniformly distributed, some buckets would have more numbers than others, and sorting them would dominate the overall computation time. In the worst-case scenario, all the numbers might fall into the same bucket.